Good morning. This is Active Filter Design, Lecture 7. In the last class, we had seen how to derive the inverse Chebyshev approximation. So, with that, we have seen how to derive a Butterworth approximation, a Chebyshev approximation, the inverse Chebyshev approximation. These are three ways of approximating the ideal brick wall magnitude response that we desire for a low pass filter. The next step, therefore, is to try and attempt to realize these transfer functions using passive elements, with the understanding that we will then replace the inductors in the passive network with some active variants which somehow kind of behave the same way as the inductors do. So, what we were looking at was the following. We assume that the source is like this, right? So, it has got some internal resistance, we call that Z0. The load is assumed to be characterized by an input impedance of Z0, and what we want to do is to insert a lossless LC network between the source and load, so that the transfer function from Vi to Vo, so Vo of S by Vi of S, is the desired H of S. So, what we need to do is to figure out what is there inside this box. And if we consider the special case of low pass all pole filters, then the ladder is a reasonable choice okay. So, the LC ladder network is a reasonable realization of the network inside, and we saw yesterday that this will give you the same number of poles as the number of reactive elements. In that sense, the LC ladder is what is called a canonical structure, because if you want to realize n poles, then the minimum number of reactances you need is n. The ladder has n inductors plus capacitors and all, which means therefore that a ladder is a canonical structure. Alright, so this is what we are attempting to do. So, find therefore the values of the inductors and capacitors inside the ladder that will result in V0 by Vi being equal to the desired transfer function H of S. Okay. Now, the question is, how do we go about doing it? Any two-port network is characterized by, it's either Z parameters or Y parameters or G parameters or H parameters or what have you. In the special case of a passive network, right? Can we say something about the parameter matrices? Pardon? If you have a passive electrical network, then any of the parameter matrices that you see, either the Y or the Z or the G or the H, the Z12 will be equal to the Z21, or the Y21 will be equal to Y12. Y11 will not be equal to Y22 unless the network is symmetric. Okay. So, in other words, at any particular frequency, therefore, this matrix, the two-port parameter matrix, is characterized by three independent numbers. Right? So, Z11, Z12, and Z22 are enough to specify the matrix. Okay. So, in other words, we need to find, one way of looking at the problem is to find Z11, Z12, which is the same as Z21, Z22, which will result in the desired transfer. Is that clear? So one way of looking at the problem is find Z11, Z12, Z21 and Z22 which realize okay. And of course, given that the network is passive, this and this are equal. Turns out that this is a difficult task, and can somebody kind of comment on why this might be a difficult task? One thing that we haven't exploited so far is the fact that this network it's a ladder, alright, but what else? If you know it is not symmetric, we don't know if the values on this side and that side are the same. The key observation is to note that the stuff inside the green box is only consisting of inductors and capacitors, and is therefore lossless. Okay. So if you have a lossless network, a very interesting observation, okay. Let's say a power P A is going into the network. Alright, PA is the power dissipated to the right of the green line. Now, what can you say about, can we make any comment about VO? Pardon? So, if we know that a total amount of power PA is being dissipated towards the right of the green dotted line, then it must follow that since there is only one lossy element towards the right, all that power must be dissipated in the resistor and not in the LC ladder. Correct? Therefore, VA is nothing but VO square by Z naught. And what is VO square? Is nothing but mod h of j omega, the whole square, times Vi square divided by Z. Correct? So what is so profound about this? So we know the mod h of j omega square we want, alright? Okay. Now we are able to relate the squared magnitude response we want not to some 4 parameters corresponding to the LC network, but to just the input power being dissipated at the left end of the box. Does it make sense? Is that clear? Okay. This is now a lot simpler problem, presumably a lot simpler problem to solve than try and figure out 3 functions of S, Z11 of S, Z12 of S and Z22 of S, which is what you would have to do if you had to have assume the general 2-port and then try and figure out the 2-port. Okay. We'd have to do something very complicated. Now, exploiting the fact that the ladder is a lossless network, we observe that all the power being dissipated, at the at port 1 of the network must be getting dissipated in the lone resistor in the network towards the right. Okay, which means that, and we know that the transfer function we want from the input to the output is mod h of j omega square, which means that if this network was realizing the filter magnitude square response we want, then it must follow that the power absorbed PA must be given by mod h of j omega square times Vi square divided by Z0. So turning things upside down, if this is what we want for the squared magnitude, then our problem reduces to finding a network such that the power absorbed as a function of frequency is given by PA, which is mod h of j omega square times Vi square by Z. In other words, what we have, and what is this? I mean, this is nothing but power absorbed by some impedance, correct? All that we need to now do is find a Zin, right, such that the power it absorbs as a function of frequency follows mod h of j omega square Vi square by Z. You understand? Pardon? No, it is not complex power. Why is it complex power? Mod h of j omega square is a very much a real quantity. Vi square is real, Z0 is real. So Pa is real power. You understand? Now, in other words, to draw a picture, I have Vi, I have Z0, and the equivalent statement of the problem is find a Zn of S so that if Pa is the power being dissipated in Zn of S, then Pa must be given by mod h of j omega square to Vi square by correct. Once we find Zn of S, what will we do? What do you think we should do? Let's say I somehow put some fight and found Zn of S such that the power dissipated as a function of frequency in Zn of S follows this mod h of j omega square times Vi square by Z0. What will I do? All that I have to do next is to synthesize an LC ladder network, okay, which has Zn of S, and at the end, I terminate it with Z0, and by definition, all this power, I've told you already that Zn has been synthesized so as to keep this power. By definition, since the network is otherwise lossy except for the resistor, all this Pa must be getting dissipated in the resistor, which means that the transfer function from the input to the output must be mod h of j omega square. Yes. Continuing from where we left off, looking at the power dissipated in mod h of in the resistor, which is a part of the Zn of S, we can conclude using conservation of energy that all the power that's dissipated in the two-port must be dissipated only in the resistor. Therefore, the transfer function from input to output must be mod h of j omega whole square, given the fact that we have found Zn of S such that the power dissipated in it is Pa, which is this expression. Is this clear? Yes? Okay. So the nice thing about this is that you have now reduced the problem of finding a two-port to to finding or determining a one port which is a single impedance. Presumably working with one port is much easier than working with two ports, because in a one port you only have to worry about Z of S, whereas in a two port you have to worry about three parameters. Okay, and what we have done is exploited losslessness of the LC network. Does this make sense so far? Okay, now let's get back to some old stuff that you know already. So if you have a network like this, what is the expression for power dissipated in the resistor in Zn of S? It is nothing but I square into R, Rn of S. In other words, it is Vi by Z0 plus Zn. Correct? This is the magnitude, this is the complex current. I will find the magnitude of the current and multiply it by the real part of Z, right? Okay, and if we deal with only S on the j omega axis, all this corresponds to standard sinusoidal steady state analysis, all the phasor stuff that you've done in your basic circuits classes. You understand? So in other words, what we need to do therefore is to find a Zn such that Vi square times real part of Zn divided by Z0 plus Zn whole square magnitude is mod h of j omega square Vi square by Z0. Is that clear? This is what this is what we wanted for the power dissipated in Zn of S. Okay, this is the expression for power dissipated in Zn, which means that we want to find a Zn such that this character is the same as this. Okay. Now, let me rewrite this in a slightly different light. Have Vi and Z0. What is the maximum power that can be dissipated in any impedance here? So the maximum power that can be dissipated in Z is Vi square by 4Z0, and that occurs when Z equal to Z. This is a very well known thing. Correct? Now, you didn't hear? Alright. Now, if the power dissipated in Z is some number, obviously which is going to be smaller than Vi square by 4Z0, then you can always relate the difference between the power dissipated in Z and Vi square by 4Z0 to what? You understand the question? We know that the maximum power that can be dissipated in Z is Vi square by 4Z0. Now, if I put some random impedance there, I found the power that was dissipated in it, then the difference between the maximum power which can ever be dissipated, which is Vi square by 4Z0, and the actual power that's being dissipated in Z should obviously be, you should be able to relate this difference in powers to we should be able to relate the difference between the maximum power that one can dissipate in the load resistor Z and the actual power being dissipated to the deviation of Z from Z0. The larger this deviation, please note that Z can be complex. Okay, so the larger the deviation between Z and Z0, the more the power dissipated will differ from Vi square by 4Z. Is that clear? Okay. Now, so let's try and figure out what the Vi square by 4Z0 is the power, is the maximum power that can be dissipated in Z. Okay. Now, the power absorbed in Z is how much? What we found is Vi square by mod Z0 plus Zin, let me call this Zin, whole square times real part of Zin. So this is the maximum power. This is the actual power. So we should be able to relate this quantity, which is the maximum power, the difference between the maximum power and the actual power, to the deviation of Zin from Z0. Okay, now this deviation is a loose term, right? It's, we have not quantified what this deviation is, right? Okay, so let's simplify this, and this is nothing but Vi square by 4Z0 minus Vi square, real part of Zin is nothing but Zin plus Zin star by 2 times Z0 plus Zin. What is the squared magnitude? You can write it as mod Z0 plus Zin times conjugate, which is Z0 plus Zin, okay, which can be written as Vi square by 4Z0 minus times 1 minus two Zin plus Zin star divided by times Z0 divided by Z0 plus Zin to Z0 plus Zin. Does it make sense? Okay. Which is Vi square by 4Z0 into 1. Let me just cross multiply and do the math. Z0 square plus Z0 Zin star plus Zin Z0 plus mod Zin square minus Zin Z0, sorry, right, plus Zin Z0 minus 2 Zin Z0 becomes minus Zin Z0, and similarly plus Z0 Zin star minus 2 Z0 Zin star becomes minus Z0 Zin star. This is, and the denominator simply remains Z0 plus Zin into Z0 plus Zin star. And what can this be simplified as? Vi square by 4Z0 times, can you look at the numerator and realize something? it's Z0 minus Zin, sorry, Zin minus Z0, I'll write it this way, into Zin, sorry, Zin star minus Z0, and the denominator is Zin plus Z0 into Zin star plus Z0. Correct? So does this, do these expressions ring a bell? Are you familiar with, have you seen expressions like this before? What is this quantity? Have you guys seen this in some other context? Yes, no? Come on, people. No? Don't you do this in EM these days? Yeah. What is Zin minus Z0 by Zin plus Z0? Okay, if you have not seen it, doesn't matter. I will denote this Zin minus Z0 by Zin plus Z0 as gamma. Right? And therefore, this fellow must be gamma star. Okay. Which is therefore Vi square. Therefore, what you can say is that the difference between the maximum power that can be dissipated in Zn and the actual power that is dissipated in Zn can be written as Vi square by 4Z0 times mod gamma square, right? And this gamma depends, as you can see, on the difference between Zn and Z0. If Zn equals Z0, gamma and mod gamma are 0. So as we expected before we did the derivation, the difference between the actual power and the maximum power must depend in some sense, on the difference between Zn and Z0, and that difference is given by not just simply Zn minus Z0, but some function of Zn and Z. Is clear? This gamma is called the reflection coefficient. For some very obvious reasons, I will describe you in a couple of minutes. One important thing to note is that gamma is a function of Zn, yeah, but Zn itself is a function of S, right, or j omega, if you like. Okay. Therefore, the reflection coefficient is not a constant number. Is not constant. It is in general a frequency dependent quantity, just like h of s, right? Gamma of s is also a function of s, and gamma of s is given by Zn of s minus Z0 divided by Zn of s plus Z. Okay. Now, since P max minus P actual is given by P max, what is P max? Pi square by 4Z0. So we just said that P max minus Pa is nothing but Vi square by 4Z0 times mod gamma square. Therefore means that the right hand side must be P max into mod gamma square. Therefore, we can look at the power dissipated in Zn as P max times 1 minus mod gamma. You understand? I mean, see, this is, this is a series connection of two impedances. So there is nothing that you have not seen here before, right? But what I am trying to draw your attention to is that even a simple network like this, right, you can look at things in a totally different light, and there is a deep physical significance here, and that is the following. The maximum power that you can draw out from the source is P max, okay, provided the load is exactly equal to Z naught. In other words, if the load is matched to Z naught, all the incident power is getting absorbed by the load. Now, if the load is not equal to Z naught, or the load deviates from Z naught in some fashion, then of all this potential power that could be absorbed by the load, some part of it is reflected back. Okay, it's just like you take a glass plate and you shine a torchlight on it. If the plate has been properly designed, then the refractive index is proper and all that stuff, you'll find that there is no reflection. You can always design a glass plate such that there is no reflection. That's the basis of this, what is called anti-reflective coating in most of these, in some of these windows. I'm sure you've done this as a problem in EM, right? I mean, the concepts are very similar, because here in networks we talk of voltage and current. In EM you talk of E and H, right? So lots of this stuff is all very standard stuff in electromagnetics in a different form. And of course there are 3 dimensions there, whereas here there is no notion of dimension of physical extent. You understand? So the physical intuition that allows us to write this is the motivation for calling gamma the reflection coefficient, because PA is the maximum available power from the source. If you have a passive impedance, you cannot draw away, you cannot dissipate more than this PA in the load, right? But if the load deviates from Z naught, then the power dissipated in the load will be smaller than the maximum power that you can possibly dissipate. And the difference between these two, in other words, you can think of this as this power is coming and then some of it I am reflecting back into the source. Okay. Therefore, the power that is dissipated in Zn of S is P max times 1 minus mod gamma square, right, where gamma square, gamma is the reflection coefficient, right, and you get the squared magnitude of the reflection coefficient. Is this clear? It might seem a little strange, this kind of approach, okay, but it's actually quite a natural thing to do, since these things come out, pretty much in a very straightforward manner when you're dealing with transmission lines. People in the early days were, transmission lines and telephone lines were all behaving like transmission lines because it's simply the physical extent of these telephone lines. So a lot of this theory, right, reflection coefficients and all this stuff is simply stuff which comes straight from transmission line theory, right? I'm sure those of you who have done transmission lines in the class have seen. How many of you have done transmission lines before in some courses that are not necessarily in EM, but also I suppose even in the power systems classes you must have done some transmission lines, isn't it? So this notion of characteristic impedance and reflection coefficient and all that stuff is there everywhere. It's nothing, nothing exclusive to this class, right, or to EM. In fact, even in the optics area, there again things are fields, and then you have gratings and all this stuff, and all these concepts also come in there. All right. So what we are therefore looking at is Pi square by 4Z naught, which is the maximum power that can be dissipated in a passive impedance when it's being driven by a source whose internal impedance is Z naught, times 1 minus mod gamma square is given by and this is the power dissipated in Zn. And what did we want this to be? We wanted this to be Vi square times mod h of j omega the whole square divided by Vi square. Does it make sense? Right? Therefore, you can relate one minus mod gamma whole square to mod h of j omega. In other words, if you want the power, if you want a given squared magnitude, then you want the power dissipated at the left end of the LC lossless network to be h of j omega square times Vi square by Z naught, right? But that, the power absorbed into the LC network can also be looked at as the maximum power available from the source times 1 minus reflection coefficient the whole square. Okay, where the reflection coefficient is some measure of deviation of the input impedance of the LC network from Z. Okay, so let's make a couple of simple observations. What is mod gamma must always be greater than 0, as greater than or equal to 0, which means mod h of j omega square must be less than or equal to 1 by 4, which means mod h of j omega must be less than or equal to. Of course, it didn't need me to tell you this, because if you had an LC ladder with both impedances being the same, then it's immediately apparent that you cannot get a voltage gain greater than half. Okay, at DC for sure, right? Okay, this is telling you that at any frequency it is not possible to get a gain greater than half. You understand? Just because the DC gain is smaller than half doesn't mean that the gain at higher frequencies cannot be. In general, if you have a network and the DC gain is less than 1, does it mean that the DC gain will be less than 1? I mean, the gain will be less than 1 at all frequencies? No, right? You can have tuned circuits where the gain can be much higher than 1 at some frequency in the middle. You understand? But this is telling you, and this is coming purely from a energy conservation viewpoint, right? Power dissipated in the network must all be in the resistor and so on. Therefore, this is telling you that if you have an equally terminated LC ladder, the transfer function from the input to the output, the magnitude cannot exceed half for any frequency. Alright? But what have we done so far? Our Butterworth filters and Chebyshev filters and all have DC gain equal to 1. But the maximum this can realize is only half. So what do? We say, okay, I'm not really interested in 1 by 1 plus omega to the power 2n in the Butterworth case. I'm happy with half into 1 by 1 plus omega to the power 2n. Okay, that's just a scaling of the y-axis by a factor of. Does it make sense? Alright. Okay. Then, therefore, that's one observation. The next observation is that in the passband of the filter, what do you expect the mod gamma to be? Well, in the passband of the filter, mod h of j omega square is close to half, or the maximum, close to the value at DC. We said that at DC it can't be greater than half anyway. So if we are satisfied with the DC gain of half, then, and everywhere in the passband, the magnitude response is close to the value at DC in some sense. In the Chebyshev case, there is some small amount of ripple. In the Butterworth case, it is kind of maximally flat. right? And same with the inverse Chebyshev and so on. So one thing we can conclude is that in the passband, mod gamma is a small number. This makes sense because all the available power from the source, if the gain is half, right, it means that all the power that's available from the source is being dissipated in the load, and that's happening, you know, in frequencies in the passband. Almost all this voltage appears across the resistor, which means that almost all the available power is being dissipated in the load, which therefore means that almost all the available power is being absorbed, which means almost none of it is being reflected, which means that the magnitude of the reflection coefficient must be small in the passband. In the stopband, what is the voltage across the load? It's becoming smaller and smaller, which means that the power being dissipated in the load is also becoming smaller and smaller, which means that, what can you say about the reflection coefficient? So in the stopband, this makes sense because in the stopband there is no voltage across the load, which means all the available power is no power is being reflected in the load, which means none of it is being absorbed at the input of the LC network, which means all the power is getting reflected back, which means the reflection coefficient is close to. Okay. Alright. So now what have we achieved? From mod h of j omega square, this is known. From this, we can go and obtain mod gamma square. And what is mod gamma square? What is gamma? Gamma is related to the input impedance Zin by Zin minus Z0 divided by Zin plus Z. Is that clear? So, in other words, let me now take an example. Let me see, take for example a third order Butterworth network. What is mod h of j omega square? I mean, the original stuff we started off was 1 by 1 plus omega to the power 6. Okay, we know that this DC gain is 1, so we say we want the DC gain only to be half. Okay, which means that we will say our desired mod h of j omega whole square is 1/4 divided by 1 plus omega to the power 6. We want a DC gain of half. Mod h of j omega maximum, we want it to be half. So mod square must be 1/4. And the usual expression for the Butterworth number, squared denominator, polynomial, the magnitude. Is this clear so far? And we want this to be equal to 1 minus mod gamma square by 4. Correct? Which means, what is mod gamma square? This 4 and this 4 goes away. Mod gamma square is omega power 6 by 1 plus omega to the power 6. As we expect, in the passband frequencies, that is at frequencies which are very small compared to the passband edge, we see that omega is a small number between 0 and 1, and mod gamma square is virtually given by is almost given by omega to the power 6, where omega is small. In other words, at frequencies well within the passband, the magnitude squared of the reflection coefficient is close to being 0. At DC, it is indeed 0, which therefore represents a maximum of transmission. Okay, and as frequency increases, you can see that the reflection coefficient keeps increasing. At frequencies in the stop band, in other words, for omega being much larger than 1, what happens to the reflection coefficient? The reflection coefficient is 1. Is that clear? Okay. Now, I mean, again, this is mod gamma square. This is that evaluated on the j omega axis. So, if you want, as usual, this is nothing but gamma of s times gamma of minus s, evaluated at s is equal to j omega. Which means that gamma of s times gamma of minus s is given by, what should I do? Replace omega as s by j or omega square as minus s square. So you get, what do you get? Minus s to the power 6 divided by 1 minus s to the power 6. Okay, and this is n of s times n of minus s divided by d of s into d of minus s, where n by d is gamma of s. Please note that gamma depends on zn minus z0 and zn plus z0. So if zn is a polynomial in a ratio of polynomials in s, it must also follow that gamma is also a ratio of polynomials in s. So it will have some numerator and some denominator. And can you notice something about the denominator? Does this sound familiar? This is exactly the same thing that we did for the Butterworth. Okay, so again, d of s must have all poles in the LHP. Alright, and therefore d of s is the third order Butterworth denominator. Is clear? And does somebody remember what the third order Butterworth denominator is? And d of s is s plus 1 into s square plus s plus 1. Okay, therefore gamma of s is gamma of s into gamma of minus s is minus s cube times s cube divided by d of s into d of minus s, where d of s is given by an expression. I mean, I was able to write out that expression because somebody remembers it. We've done it before. Same thing. We find the roots of 1 minus s power 6. Okay, there will be 6 roots. We associate the LHP roots with those of d of s and discard the RHP roots. Okay. Now, can somebody tell me what gamma of s is? Well, there are two possible solutions. One is s cube by s plus 1 into s square plus s plus 1 or minus s cube by s plus 1 times s square plus s plus 1. Fine. And now, given that we know gamma of s, this is nothing but Zn minus Z0 divided by Zn plus Z0, which can be written as Zn by Z0 minus 1 divided by Zn by Z0 plus 1. Okay, and that is equal to either this chap or this chap. Let me handle this case first. So, if Zn by Z0 minus 1 divided by Zn plus Z0 plus 1 is given by that expression which has been circled in green, it follows that Zn by Z0 is what? The 1 plus gamma by 1 minus gamma, and what might that be? You have gamma, please compute. D of s, if I simply expand it out, is s cube plus s square plus s square plus s plus 1. So what is gamma? What is Zn by Z0? 2s cube plus 2s square plus 2s plus 1 divided by 2s square plus 2s plus 1. Alright. Okay. In other words, this we have expression for Zn by Z0. In other words, this expression on the right hand side is the normalized input impedance that the LC network loaded by the 1 ohm by the Z0 must present to the input in order that the power dissipated in the LC network and the load is what we want, which means that the transfer function from input to output is mod h of j omega square. You understand? From the required transfer function and the losslessness of the LC network, we have derived the power that needs to go in to the LC network. From the power that needs to go into the LC network, we find the reflection coefficient looking in. The reflection coefficient is a measure of the deviation between the input impedance of the LC network terminated in the resistor Z0 and Z0 itself, right? Which means that we can go and find Zn as a function of S. Okay, and now given Zn as a function of S, we presumably can go and find the network given its form. We already know it's a ladder. Correct? So, and for convenience and to keep avoiding to have to carry Z0 everywhere, we from now on assume what? I mean, you can choose choose any particular value, the most convenient value is Z0 equal to 1. Okay. Alright. Please note that Z0 equal to 1 is not a practical value at all. You will never make filters with Z0 equal to 1. Now, if you suddenly find that you want Z0, your source has impedance of 253 ohms, what will you do? Will you go through all this all over again with 253 ohms, or will you do something smart? You just have to scale all impedances up by that number Z0. Okay. So, in other words, whatever impedance you get here, or whatever values for L and C you get here, for an arbitrary value of Z0, what will have to happen? L will get multiplied by Z0 and C will get divided by Z0, so that all the impedances have been scaled by the same factor. Okay. So, in other words, the Zn we are interested in realizing as a function of S is 2s2 plus 2s square plus 2s plus 1 divided by 2s square plus 2s plus 1. Okay, and the Zn that we are referring to is that of the LC network loaded by D. Now, can you stare at this expression and tell me? I mean, this is clearly a third order ladder, right? So the ladder can be of, these are two ways of realizing a third order ladder filter. So there are 3 L plus C. Okay. On the other hand, the pi network is also a candidate which can realize a third order transfer function. Okay. Which do you think gives the one on the left, and why is that? Yes, Ashwin Ram, what do you think? So what? I mean, if you're not happy with the number of inductors in the second network, I'll add. Does that change your answer? No. No. So, okay. Much more low funda than that. Yeah, so what? Why should the, yeah, I understand that if you divide numerator by denominator, you will get some S. Yes, all this is correct, but that still doesn't explain why it is the first network. The first network has 2 inductors, 1 capacitor. The second network has 2 capacitors, 1 inductor. Inductor is S, capacitor is 1 by S. It is all correct, right? But that still doesn't convincingly prove that it must be the first network. No, not really. What are you going to do? Once you find which network, you're always going to have the source in series with the resistance. That's not also correct. Huh? No. Huh? At very high frequencies, what is Zn of S? How does it behave? No, okay. What does this expression tend to as at very high frequency? Okay, it is infinity, but it goes as S, correct? And which of these networks at very high frequencies, right? What are the equivalents of this network, this network? At very high frequency, the inductor becomes, this becomes open, this becomes a short, right? So at very high frequencies this network looks like an inductor. You understand? Whereas at very high frequencies this becomes an open, this becomes a short. So this network will look like a capacitor. You understand? Is this clear? It's got nothing to do with the number of inductors and the or the way they are connected. Okay. T, pi, all that stuff is irrelevant. Please note that any arbitrary impedance, okay, Zn of S, which is physically realizable using passive elements, lumped elements, will at very high frequency look like one of the three. What are they? I mean, any impedance at high frequencies will look like either like a capacitor, like an inductor, or a resistor. Okay, this can be proved rigorously, but I mean intuitively I think it's obvious. Okay, so this is the network that corresponds to Is that clear? Okay, now that let's call this L1, C2 and L3, and the last one Z0 we have assumed to be 1. Correct? So, as we just reasoned, as S tends to infinity, Zn of S tends to Zn of S tends to S, and in the network it must tend to SL1. Does it make sense? Correct? Which means L1 must be 1 Henry. Okay? Alright. So, we know this. What are we now therefore interested in finding? We are interested in finding the C2 and L3. So, we know L1. So, in other words, we know we should be able to find the impedance looking in to the right of L1. Correct? And what would that be? That would be Zn of S minus L1S, which is 2S cubed plus 2S square plus 2S plus 1 minus S square plus 2S plus 1 times S divided by 2S square plus 2S plus 1. Does it make sense? Again, what is this? S plus 1 divided by 2S square plus 2S plus 1. Okay, and this must therefore be the impedance of this network. Correct? And why does this make sense? This makes sense because at very high frequency, how does this look like? It looks like 1 by SC2, okay, Okay, and very high frequencies, what does this expression reduce to? 1 by 2s. Okay, all right. In other words, what we can in fact say is that this is z in 1 of s. Okay. Earlier we found that z in of s tended to infinity at s is equal to infinity. In other words, there was a pole of z in of s at infinity. Once what we have done by removing L1 of s is to remove that pole. Okay. So clearly there is no pole at infinity for z in 1 of s. However, we see that because the leading element is a capacitance, y in 1 of s. What is the admittance looking in now? 2s square plus 2s plus 1 by s plus 1 is the admittance looking in, and as s tends to infinity, this admittance tends to 2s, and this must be equal to SC2. So what must C2 be? You understand? So now what should I do? I need to find L3. So I can find the admittance after C2. The admittance before C2 is 2s square y in 1 of s. This minus s times C2 must be y in 2 of s. And what will that be? 2s square plus 2s plus 1 minus s plus 1 into 2s divided by s plus 1, which means y in 2 of s is given by 1 by s plus 1, which means that z in 2 of s is s plus 1. And what is z in 2? Correct? And therefore L3 must be equal to 1. Okay. So the LC network that results in a transfer function which is a third order Butterworth. This is 1, this is 1, this is 2, this is 1 ohm. Yes, sir. No, but at DC, the magnitude is half if you have both equal terminations, isn't it?